Yes, sir, you can start, sir. Okay, he wants to do an introduction. Tell the audience about yourself, why you're here, what's the purpose of your position upstage, and then begin your presentation.
My name is Mr. Stephen Harrington. For those who don't know me, I was raised and whipped by the British. This is my presentation on impact toughness of metallic materials. You, sir, looks like you want to beat me up. Do you want to beat me up?
Yeah.
You know where to find me. Background of experiment. Most material properties change gradually as temperature is reduced. Some properties have been found to exhibit dramatic property changes over small temperature ranges. Example, Cleveland Susan. Anybody, Cleveland Susan. It's right in front of you. Carbon steel. A ductile to brittle transition is one such property change of engineering importance. Testing for this temperature transition can supply useful data to prevent failure of material in its application. Purpose of experiment. Charpy impact test is the most simple of all testing procedures used to determine the toughness of a material. It provides several properties of materials such as toughness, ductility, and fracture characteristics. Since the test represents a high strain rate and the transition temperature is raised by increasing the strain rate, the maximum transition temperature is obtained. Using this characteristic of the material design criteria helps to ensure that the structure will undergo brittle failure. We use the Charpy pendulum impact test. Energy transfer to the material can be inferred by comparing the difference in the height of the hammer before and after. Energy is measured in foot-pounds or Newton-meters. Tough materials absorb a lot of energy, while brittle materials tend to absorb very little energy prior to fracture. The Baja team come crying to me because you don't test your materials right here. Forget your boundaries and conditions. Get that. First material, Cleveland Susan. Anybody? Carbon steel 1045. Known as a medium tensile steel containing 0.45% carbon and a maximum of 1% manganese. Silicon content will range from 0.15 to 0.3%. Provides good balance between strength and ductility. It's strong. You push me, I don't move. Very strong. Good machinability, it normalized as well as hot rolled conditions. Commonly used in axles, bolts, connecting rods, hydraulic clamps, and rams. All these vehicles you drive around in, carbon steel 1045. Microstructure for steel. Body-centered cubic. Has 8 total lattice points on 8 corners and 1 unit. This yields 2 lattice points per unit cell, 1/8 times 8 plus 1. 2 atoms per cell, the atomic packing factor is 68% of the volume of the unit cell. Next material, Allen, 2024 T35. Anyway, Allen, aluminum alloy. Primarily alloy with copper, 3.9% to 4.9%, and some small amounts of manganese, 1.2% to 1.8%. Solution heat treatment and stress relieved by stretching. You take a pizza, you put it in the oven. Heat treatment. Good strength to weight ratio. It has ductile and excellent fatigue resistance. You push me, it bends. You push me, it bends. Commonly used in aircraft, structural components, truck wheels, medical instruments, and screw machine products. All those Airbuses in the sky. Aluminum alloy. Microstructure. Aluminum alloy. Face-centered cubic. 8 atoms located on the corners, and 6 atoms on each face. Total number of lattice points are 14. Therefore, there are 4 lattice points. 1/8 times 8 plus 1/2, 6. Atomic packing factor is 70% of the total volume of the unit cell. Energy absorbed by material at each temperature starts at negative 186 degrees Celsius to 188. First material, carbon steel is on the left, aluminum alloy on the right. This is the coldest temperature, very brittle fraction.